model he built up. It was very fun when he visited us in Oxford. We really hit it off. So, from our perspective, we're interested in risk, and here is one which I'm going to show in more detail later. So this is the sizes of war. So this is how many people, or how many thousands got killed in different wars. Power law distributed. This is the number of victims in terrorist attacks. Okay, and this is the sizes of power blackouts. A lot of power laws here. And again, there are some pretty interesting reasons to believe that big events tend to be power law distributed. There is something called the extreme value theory, which is used a bit in finance and quite a lot in insurance. Because it turns out that the tails of probability distributions, if they are to be stable, they can only be of 3 different kinds, and one of the kinds is a power law, and that seems to happen an awful lot of the time. So you can actually use this, and this is being used, for example, in thinking about if I want to build a flood protection for the Netherlands. Okay, I got some data here for the previous century of how big the floods have been. Okay, I want to predict for a 1 in 100,000 year flooding. I haven't got data for that, but I can use these models to estimate the probability of that and the size of it. So that way I can actually build a flood wall that's high enough. With me so far? Yeah?
What was the third type? Is it one was a power law, so, and was it exponential, presumably?
In the case of a stable distribution, it's a bit confusing because they're called the Weibull, Fréchette, and Gumbel distributions. The Gumbel distribution is essentially the odd cousin of a normal distribution, while the Weibull distribution is what happens when there is actually an upper limit to how big things can be. And that's very interesting also from a disaster perspective, because we want to actually figure out whether there is an upper limit for some kinds of disaster. So having a test that can distinguish between the Fréchette and the Weibull distribution in this case is very important.
And the sets you're looking at there, just to pick one to illustrate a point, the surname set, it's obviously on the line and then it starts to deviate and become a bit chaotic and off the line. Is that predominantly because, do you think if you have more data then you get pretty much on the line as well? Is it because people, at that point you've got like one person in the world with that surname, so obviously it's the data sets that you're working from obviously don't list everybody's surname on the entire planet, so you only have the large.
But suppose we had the ultimate phone book that actually contains everybody's true name. We would still see something down at the tail because there is only one person named the @ in the world, as far as I know, for example. So down here you get the extreme events which you don't have much data for. And there is of course always a chance that you're going to get a serious deviation. So this is web hits, for example. And well, it follows a power law here, maybe here, but they're only in different domains. But probably that the sites that get a ridiculous number of web hits are quite different from the ones that get a normal number. So it's not always true, and sometimes you get important deviations. So I think I'm going to get into this more detail. So this is earthquakes. It turns out that the really biggest ones, where people have been working quite a lot of this one, they know that it's going down much more steeply. There is an upper limit, of course, to how big an earthquake could be, because there is only so much energy to go around in the crust. But then there is another thing up here, because here you got a measuring problem, because most of the really weak earthquakes you can't even measure. So sometimes these deviations matter quite a lot. That is of course a big problem, because a lot of people just love plotting stuff on log paper, and usually almost anything looks roughly like a line, which means that we rush off and publish a paper about it. So I've been working quite a lot based on a paper by Newman and Cosma Shalisi about how to do power law estimation. And Shalisi has a great web page called "So you found the power law? Oh, how special isn't that?" It's a wonderful, very cynical and very refreshing look at how to actually try to check, is this a true relationship, or is it just that I plotted a few data points. So the interesting thing is of course when you can apply this to various things. So this is data losses. So there is a wonderful database about when companies losing laptops, CDs and memory sticks with personal information. So this is the number of records they accidentally misplaced somewhere at a pub or so, and this is the number of cases we should expect per year. So smaller ones, like losing, let's say, 100 customer names or so, that happens at a rate of a few thousand each year. And then, of course, we're getting over to this corner where we have like famous British successes like those 25 million names of kids and their families and their banking records on a CD that nobody knows wherever it ended up. So the biggest case here, actually, it got 100 million people roughly on it. The interesting thing is that thing seemed to, based on this kind of fit we've done here, to occur with a chance about, well, every 5 years. We should expect that about every 5 years we get 100 million personal data sets well, lost, which is pretty interesting. If we continue this line, if we assume it can continue, and I think we don't have any reason to believe it can't continue, we could imagine that down here we got, of course, 1 billion, and that's probably going to happen in terms of. The only thing that's causing a cutoff is probably that nobody got a data set of a billion people yet. I'm pretty certain the NSA and Department of Homeland Security are trying to compile that. I know they're actually running agent-based simulations with literally billions of agents. So maybe in a few years they accidentally misplaced that little nice terabyte data set, and well, it ends up in the hands of spammers.
We need China already used Neuroethics, basically.
Mm-hmm.
Billion.
Yeah, yes, exactly. So the interesting and scary thing is the data losses are already enormous, and this is again a risk that's going on, and most people don't really notice that it's serious. Right now it's not serious because most identity theft people can't make use of a billion names. Suppose we could figure out a way of automating that. Then we would have some really scary effects. Here's another interesting data set, and this is about power outages. And they also tend to follow a pretty good power law when they're pretty big. The small power outages are caused by a lot of random factors. The big ones seem to be network effects. You have a very complex power network, and it fails for some local effect, and then you get a spread across the network. The problem is, it turns out that, well, you can get pretty big power outages. So, and especially the restoration time can also be pretty long. If we lost electricity for 1 hour, this would be slightly annoying. I could probably do most of my talk standing here in the shadows. It would be annoying. If we lost power for 10 hours, well, London would be in trouble. People would find a way to use a stiff upper lip and get around, but it would be messy. If you get 100-hour power outage, now we're really in trouble, because by now the amount of fuel to run a lot of generators is going to run out. And if you also get a distributed power outage, you can get a lot of problems. So in southern Sweden, a big storm, for example, broke a lot of power lines. And that crashed the phone network a day later, because all the phone stations were running on this kind of localized fuel, but the fuel trucks couldn't get to them because there were trees in the roads. So they stopped, and now there was no communication in this otherwise advanced and nice area. That was not very good. So the problem here is the probability of getting a very long and very big power outage is unfortunately not terribly low. I haven't got the numbers in this one, which is a bit of an oversight. We know they have a power outage which have been roughly the size of the power grid in developed nations in recent times, which actually should lead us to consider that this is something we should seriously consider what to do about. Then of course we can use external factors to add a bit of more angst to this. There have been this discussion about solar superflares, which would indeed have a big effect, because they would cause a lot of correlated overloads, which is very bad for any system. Well, what else do we have? Well, this is dead from tsunamis, and it seems to follow a rough power law, but there is of course an upper limit how many can get killed, simply because not everybody is close to the ocean. But still, given that a lot of people are living close to the ocean, we should be concerned. Volcano deaths have an even more steep decline here. The power law works well for the small ones, but, well, the really big ones. But again, something can become very different. If we got a super volcano, suddenly everything would go global. Then we would get a very different curve, but a lot more people would be in danger. Similar for flooding, it's also pretty local. And also shows the problem with this kind of data, because that's actually the Boxing Day tsunami, so it was also in the tsunami plot. Nick Bostrom is constantly haranguing me about this data. He wants every data point in one of the plots and not in several of them. But it's sometimes very hard to actually disambiguate them. So then, of course, we have issues